We'll wait for a few minutes for others to join.
Hello, sir. Good evening.
Yes, good evening, Santosh.
Today is the last week of
I'll, I'll,
problems.
I'll let you know. Let's wait for others.
Okay, okay.
All right, let us start. So, welcome everyone to the week 12 tutorial for the course IC Engines and Gas Turbine. And this will be your last tutorial for this course. Uh, I hope everyone has been efficiently regular to your tutorials as well as the lecture videos and the assignments. Those who have registered to participate in the exam, I expect that everyone had uh, gone through thoroughly through all the videos and the assignments on well on time, submitted them. So today we will start with the further centrifugal compressors. Okay. In the last tutorial, we finished with the principle of the rotary compressors. Okay, so in rotary there are two kind of compressors, centrifugal and axial flow compressor. And with this we will finish our course as well. So let me start. Share my screen. I hope I'm audible. Can anyone confirm?
Yes, sir. You are audible.
My
You are audible.
and my screen is visible to everyone.
Yes,
Clearly.
sir.
Yes, sir, visible.
Okay, thank you. Let me know at any point of time if you don't hear my voice or screen breaks off immediately. And I hope if you were able to see the lecture videos as well as tutorial videos from my YouTube channel Nptel with Varnit, and other those who have registered in the course, they are able to get the Google Sheet from the NPTEL team. All right, so in the principle of rotary compressor, we came across with the impulse effect, centrifugal effect, and the diffuser effect towards the last. Now let us particularly talk about the centrifugal compressors. Let me write here. centrifugal compressors. So basically, these are radial flow compressors. So the fluid flow in a radial direction from inlet to outlet, and air enters at the eye of the impeller in axial direction and moves through the impeller in radially outward direction. As well as the inlet casing, inside the inlet casing, there is a little pressure drop along with the increase in the velocity. And after that, the working fluid is flown through the impeller, in which energy is transferred along with the increasing the static pressure when it passes through the casing. And also there is increase in kinetic energy, and the above kinetic energy is converted into pressure energy in the diffuser. Okay, and which is known as a energy transformation process. So generally the compressors are designed in such a manner that 50% of the total pressure rise happens inside the impeller and rest 50% happen inside the diffuser. So I have discussed in detail what was impeller diffuser when I draw the diagram there, schematic diagram. So you can refer that diagram. So, and there are some dimensions which we will notate with. So let us say your D1 and D2. These are basically our impeller or rotor diameters at inlet and outlet. Rotor or impeller diameters at inlet and outlet. Okay. And these are also called as D1 is also called as hub diameter or rotor diameter, and D2 is also called as tip diameter. That is why you have U1 and U2 velocities. Then B1 and B2, B1 and B2 are your rotor width, sorry, are the width of the impeller at inlet and outlet. Width of impeller at inlet and outlet. Then K1 and K2 are the coefficients at inlet, area coefficients at inlet and outlet. Area coefficients, sorry, blade area coefficients. Blade area coefficients at inlet and outlet. Then N is the number of vanes, because on a single rotor there are number of blades or vanes are there. Number of vanes, and T is the thickness of each vane. Thickness of each vane. Okay. So let me help you to visualize this. How does it look like? So you have a eye here. That is your rotor basically. Okay. Then there are multiple number of vanes attached to this. Okay. And this is again covered with a, this whole setup is called as an impeller. Okay. This whole setup, I'll not make all the vanes. Okay. So this whole setup is impeller, which is moving. Okay. Which is moving. And it is again connected through a diffuser where you have fixed vanes. Okay. So there was a diffuser with a diverging section, which I made in the previous tutorial, the diagram. And if you see from the center, you have D1 diameter, D2 diameter, that is at inlet and outlet of the vane. Okay. Inlet and outlet of the vane. Now, if you see, let me draw one specifically vane out of it. So I have a vane like this. Okay. Let us say I made a bit. Let me make again. This is vane. This vane So this was position 1, let us say, and this is position 2. Okay, so this is position 1 and this is position 2 of a vane. You are visualizing it from a top view. Okay, so water entered from the eye of the impeller and it transferred radially. Okay, along this radius. Okay, water transferred along this radius or air, whatever you are compressing. Okay. So B1 and B2 are the width of the impeller. So this is B1 and this is B2. B2. These are the width. It will look something like this if you see from the top. I'm just trying to make it isometrically top view. And then D1, D2 I have told, B1, B2 I have told, N is the number of vanes, and T is the thickness of each vane. So this will be your thickness. Let's see. This is your thickness of the vane. Okay, T. So what will be the area of at the inlet of the impeller? So inlet of the impeller means this area, that is, and there are n number of vanes there. It is not a single vane available. So at the inlet of the impeller, area will be complete pi d1. The circumference is pi d1 of this complete impeller at the outlet, and at the inlet it is pi d1. At outlet it is pi d2. Okay. So this is your diameter and this is your d. I made mistakenly the radius. So d1 and d2 are this. So area will be pi d1 minus the thickness of each vane, because this each vane is also taking some area inside it. Okay. So circumference into the width. So pi d1 minus n into t, thickness of each vane, and n is the number of vanes. This is the total circumference at inlet in times width, that is b1 times b1. And this can be written as k times pi d1 b1. Okay, that's why I took it as a k as the blade area coefficient. We can simplify it like this. Similarly, a2 will be pi t2 minus again n times t, thickness is t. We are taking, you can say we are taking mean thickness at that point of stage. Okay, you can talk in terms of mean thicknesses as well. So area is pi times d2 t minus nt times width b2. So again it will be k2 pi d2 b2. Okay, so this is the area of the water in contact. So water will be in this region only, inside this circumference, because the blade vanes are made up of some metal and they are taking some area inside the circumference. That is why we have to subtract, that is from the pi d1 minus thickness of each vane multiplied by the number of vanes times the width. Width area is width into circumference. All right, these are the areas. So I can say that these areas are nothing but area of contact of water. Total area of the contact of water. So I was talking about the working principle here. I hope this is visualizable. Everyone is able to visualize. The working principle says that in centrifugal compressor, or you can say a radial flow machine, see why I am saying it as centrifugal. Suppose I want to help you visualize it from the front view. Let me show you. So this was your complete rotor. On the rotor, you have vanes, okay, attached to it. Okay. So this was your, which you observed from it was I from the top, but from the front it will look like this, and it is moving like this, you know, like this. Okay, at omega, suppose subspeed, the complete setup was moving like this. Okay, so as soon as the water entered at this point, it entered radially as well as it exited also radially. That is why it is called. But if water would enter axially, axis is along this rotor axis. It is not along the axis. It is along the blade radius, okay, or the vane radiuses. That's why it is called as a radial flow machine. Radial flow machine. Air enters at eye of impeller in axial direction. Axially it entered and moved through the impeller in radially outward direction. Impeller in radially outward direction. Okay. In inlet casing, there is a little drop in pressure along with increase in velocity. And after this, the working fluid is flowing through impeller, because as soon as you lifted up a stationary fluid which was in the sump, you started your compressor, it's actually entered into the eye of the impeller because of the vacuum process happened. Kinetic energy was higher, velocity was higher, and from the rest, that is why there was an increase in the velocity as well as decrease in the pressure. Okay. After that, this working fluid is flowing through the impeller. After this working fluid is flowing through impeller, in which energy is transformed sorry, not transformed, transferred. Energy is transferred along with increase static pressure. And there is also increase in the kinetic energy. Okay. And the, and where in kinetic energy, which term will come? Absolute velocity. We had flow velocity and world velocity are the components of the absolute velocity. So in kinetic energy, you will always say you will always talk in terms of absolute velocity. Okay. The above kinetic energy, that is your V2 was higher than V1. Okay, because it rotated over the impeller. And that kinetic energy is converted into pressure energy as it passes through the diffuser. The above kinetic energy is converted into pressure energy in diffuser, which is known as energy transformation process. Why? That V2 velocity was higher than V1, and then that V from point 2, the fluid enters into the diffuser. Diffuser is nothing but the fixed casing of the fixed blades, okay, in the diverging section. So if the diverging section is the section, if the section is diverging, that blades are in a diverging section, diverging way, Then the fluid enters, the area increases and the velocity decreases. Okay. So what happens generally? Then the kinetic energy is converted into the much increase in the pressure. So generally compressors are designed in such a manner that 50% of total pressure rise is obtained in impeller and rest 50% in diffuser. Now you may have another question like why 50% rise in and why not 50% rise directly in the impeller itself? Why do we need an extra casing of diffuser for much increase in the pressure? You can do that. You can have an impeller without a diffuser and you can increase. But because of such high velocity, okay, and high pressure increase, if you say that I want to increase the pressure 100% pressure inside the impeller itself, what will happen? The impeller blades will experience a high amount of stress. If you have seen in your design course or strength of material course, the stress is nothing but over a vane is nothing but pressure into diameter to that of 4 times of thickness of the blade, PD by 4T. If the pressure itself is very high, 100% high in the impeller itself, the stresses generated will be very high, which is not required from the strength point of view of the machine. That's why we do from that point of view. So how we will make the pressure velocity diagram for this? Let me draw. So here I'm going to plot pressure. Yes, I use around. So above will be pressure and below will be velocity. So initially when the fluid enter, it was at constant atmospheric pressure. Okay. P naught is equal to P atmosphere. Okay. And velocity of the fluid was zero at that point of time. We can say velocity was zero during the entry time. Okay. P naught is equal to zero because velocity was the fluid was collected from a static field. Okay, at the rest. Then the pressure got dropped because of the increase in the velocity. Okay, velocity increased as you started the machine. Velocity increased at the inlet. Velocity increased. Velocity increased, let us say, to the point V1. Okay, and the pressure got decreased. Pressure got P1. Okay, pressure got decreased. So this was the case of the inlet casing. Inlet casing. This happened inside inlet casing region. Okay. Now we come to the impeller region. Impeller. So what happens inside the impeller? The velocity increases further and the pressure also increases there. Okay. So velocity increases further as well as the pressure also increases. That 50% pressure is increased here to pressure P2, velocity P2. Okay. And the impeller is a work absorbing device. Your compressor is consuming the energy eventually. You are providing electricity. Okay. And then further, the velocity as it moves through the diffuser in the diffuser region towards the last, the pressure further increased, but the velocity decreased. Okay. Next 50% of the pressure was increased here, P, and velocity was decreased because the diffuser is at rest situation. Okay. And it is almost equal to the impeller inlet velocity. Okay, that is V3 is almost equal to V1. Okay, almost. All right, simple, simple as that. To remember, I'll give a short way: above tick and reverse of the tick. Okay, you can remember this like this: pressure velocity. So this is a tick and this is a reverse tick. Okay, if you even forget at any point of how the pressure velocity diagram is like. Now let's come to the stagnation state. I hope this is clear. Any doubts, Leha? Yes or no? Santosh? Doubts? Shanmugam? Do you have any doubts?
No, sir.
Okay, great. Now let's come to the stagnation state. What is a stagnation state? From the word itself, that means something is coming at the stagnation, something is coming at rest. It is basically a reference state to present the total energy of the fluid at that point. Okay. So this is a state of the fluid is obtained when it is brought to the rest condition isentropically. Okay. The state of the fluid state of the fluid, either gas or liquid, is obtained when it is brought to rest condition isentropically. That is reversible adiabatic. In case of energy transformation, the stagnation enthalpy remains constant. Energy transformation like in new nozzles or diffusers. So I've discussed this nozzle, diffuser, compressor, turbines kind of scenario in my thermodynamics course also. How the enthalpy remains constant, how the enthalpy is sum of work plus an enthalpy change is sum of work or velocity changes, and so on. Process enthalpy remains constant. Again, you can see those tutorial videos on my YouTube channel again, Nptel with Varnit, in the playlist of thermodynamics. And in case of energy transfer process, this was an energy transformation, and another process is energy transfer. In case of energy transfer process, I've missed here, energy transformation process. Okay, the it increases for compressor and decreases for turbine. It increases for compressor and decreases for turbine. I'll just give you a short glimpse here as well. Suppose I'm talking about nozzles or diffuser, or let us say diffuser. Okay, so from steady flow energy equation in thermodynamics, your sum of enthalpy, sum of energies is nothing but constant. So sum of enthalpy plus kinetic energy at inlet plus potential energy at inlet plus heat in any heat interaction is nothing but sum of enthalpy at outlet, kinetic energy at outlet, potential energy at outlet plus any work done. Okay, so let us say that diffuser is kept at the same datum level, so there is no change in the potential energy. In diffuser and nozzle, there is no heat interaction or work interaction because they are not heat or work producing or absorbing devices. So we can say that our this term, this term, this term, and this term is zero. Only there is a change in the kinetic energy. Okay, so let us say it is H1 plus kinetic energy 1 is equal to H2 plus kinetic energy at 2. Okay, so let us define by the state H naught 1, that is nothing but H1 kinetic energy is V1 square by 2 in terms of specific terms I'm dealing. That is divide by mass. Okay, specific enthalpy and specific kinetic energy. H1 plus V1 square by 2, and it is nothing but equal to H2 plus V2 square by 2. Okay, H1 plus V1 square by 2 is equal to H2 plus V2 square by 2, and it is equal to H naught 2. So what do I mean by H naught is basically your stagnation scenario where your velocities are zero. Okay, your velocities are zero. H naught is that. So your velocities inlet and outlet at 1 and stage 2 both are 0. So H naught, that is why I've written enthalpy naught at the first is nothing but equal to enthalpy naught at 2. Okay, so H naught 1 is equal to H naught 2. Or H is in terms of your ideal gas is basically enthalpy is a function of temperature for an ideal gas. So you can write Cp times T naught 1 is equal to Cp times T naught 2. And Cp for our ideal gas, let us say it's constant. So this cancels out for both sides. And this is nothing but equal to temperature naught 1 is equal to temperature naught 2. Okay, this is what I mean from the nozzle or diffuser. Let us come to the scenario of compressor or turbine. Compressor or turbine. So these are either work absorbing or producing devices. Again, from steady flow of energy equation, H1 plus kinetic energy at 1 plus potential energy at 1 plus heat interaction is equal to H2 plus kinetic energy at 2 plus potential energy at 2 plus work interaction. So let us say again they are at the same datum level. So there is no change in the potential energy. Q1 is 0, let us say. There is no heat interaction in a compressor or turbine. Only this, it's a work producing or absorbing device. So again, we can write in terms of H1 plus kinetic energy 1 is equal to H2 plus kinetic energy 2 plus work. Because if it's a work producing device, the work will be absorbed, negative work. If work producing device for a turbine, it will be a positive work. Okay. Again, I'm saying H1 plus V1 square by 2 is equal to H2 plus V2 square by 2 plus work. And in terms of stagnation, my V1 and V2 will be 0, 0, and 0. So that is nothing but your H naught 1 is equal to H naught 2 plus work. So if it is a compressor, it is nothing but H naught 2 minus H naught 1 because temperature will be higher at the outlet. And if it's a, so eventually the enthalpy will be higher. Whereas for a turbine, it will be H naught 1 minus H naught 2. The energy or enthalpy at the inlet of the turbine should be higher, then only it can produce the work. Okay. So in compressor, it is 2 minus 1, in turbine, it is 1 minus 2. So basically what we are doing, we are saying that stagnation state is a state. Its work as a reference to present the total energy of the fluid at that particular point. Okay, at that particular point. So what do I mean again is that the total energy at the inlet was H1 plus V1 square by 2, but we made V1 to be 0. Okay. And what do I mean? What do we mean by that is that we already added the V1 energy in the enthalpy itself. Okay. Okay. And brought our fluid to the rest condition. So let me write a note point here. Stagnation state works as a reference system to present the to represent the total energy of fluid at a point. Okay. So if I have a complete compressor scenario, I have an inlet casing, I have an impeller, I have a diffuser. Okay. So if I am having a compressor, so I have inlet, casing, I have an impeller, I have a diffuser. These are the three things. Okay. This was condition number where the fluid entered, condition 0, 1, 2, and 3. Okay. Work was input at this stage, work input. Okay. So in the inlet casing, what happened from 0 to 1 stage, from 0 to 1 stage inside the inlet casing, your H01 was nothing but H1 plus V1 square by 2, or you can say that only H1 plus 0 square by 2. Okay. In impeller, when you are talking in terms of stagnation, it will be H1 plus V1 square by 2, no change in the potential, no change in the heat interaction, is equal to H2 plus V2 square by 2 minus the work input, because work has been provided, negative sign. Again, you make the stagnation scenarios. So it will be H01 is equal to H02 minus work input. So work input will be H02 minus H01. This is your work input. And this can be written as Cp times T01 minus T0, sorry, T02 minus T01. T01. This is your work input to the impeller, or basically your compressor. Again, in the diffuser itself, if you go for the state 2 to 3, again your H0, H2 square, have I written something? All right, H2 square plus H2 plus V2 square by 2. No heat or energy interaction, H3 plus V3 square by 2. Again, make it in terms of stagnation, H02 is equal to H0. So this will be your scenario for all the three parts of your complex. Now let us make a velocity triangle here. We'll come to the section of velocity triangle. Any doubts still here? Velocity triangle. If you have any doubts, please ask. So I want to talk about the velocity triangle here. So let us assume that at the inlet of impeller, fluid is always entering in a radial direction. Okay. When I said that at the impeller, it came axially, but it was not complete axial. It was having some v1 velocity, absolute velocity, which had a component of whirl as well as an axial flow direction. Okay. So let us say that whirl component is completely zero. Whirl component basically defines the change in the magnitude of the absolute velocity, and the flow component decides your direction to move in a circular direction. Okay, to maintain the direction. So I say that at the inlet of the impeller, fluid is always entering in a radial direction. Okay, that is your flow direction, and your whirl component is zero. Okay? We will assume like this all the time. So let us say, assume that at inlet of impeller, fluid always enter in radial direction. That is, whirl component Vw1 is equal to 0. Okay. What is the function of a forward curved blade? The forward curve, there are three kinds of curves in a blade are there. The blades or vanes which are attached to the impeller. Either they can be radially curved, they can be forwardly curved, or a backward curve. Okay. So for a forward curved blade, it produces high pressure but have a lower efficiency, because efficiency is nothing but the pressure ratio minus 1 to the power of pressure ratio power n minus 1 by n minus 1. We have already calculated the work expressions for the compressor, and efficiency is nothing but your work turbine minus work compressor by heat supply. Okay. So if the pressure ratio is high, efficiency is going to be eventually low. Whereas the backward curve vanes are opposite to it. They have a better efficiency but have lower pressure ratio. Okay. So we have to come in a midway of both of them, neither forward neither backward nor backward. So we came across with the radial curved planes because they produce a balance of it, and they are preferred because centrifugal effect of the blades creates a when you have a centrifugal effect, they creates a bending moments and develop high stresses that may damage the blade profile. So radial blades are always preferred. And if nothing is mentioned in the question by the examiner, what kind of blade is given, then you have to always assume it is a radial blade. Always assume it is a radial blade. Let me write forward curved blades produces higher pressure ratio but have lower efficiency and narrow operating range. Whereas the backward curved screens have better efficiency and wider operating range. Okay. Radial curved blade are preferred because centrifugal effect of curved blades or vanes creates bending moments. So you have to always see from design aspect also of the machinery. Creates bending moments and develop high stresses which may damage the blade profile. Therefore, radial blades are always preferred. Already I have written radial blades are preferred because okay. And if nothing is mentioned in the question, you have to assume the radial blades at the outlet. At the outlet. Let me write. If nothing is mentioned in the question, always assume radial blades at outlet. Okay. So backward curved vanes have the vane angle phi is less than 90 degree at the outlet. Forward one has the blade angle phi greater than 90 degrees, whereas a radial blade has a blade angle at the outlet phi is equal to 90 degrees. Okay. Let me draw the figures as well of the outlet. The first one is backward curve, where your phi is less than 90 degrees. Okay. Phi is less than 90 degrees. Okay. Phi is less than 90 degrees. So for inlet, I have already told you have to assume that it is have wall component 0. So how it will look at the inlet? Let me also make the diagram for the inlet also. Suppose you have a vein like this. It will get bigger. Okay. So you don't only have a flow component and it is equal to your absolute velocity. Okay. You have a u velocity at the inlet u1, and from the triangle of addition the relative velocity, because blade is also moving, it will be vr1. Okay. This is your inlet velocity triangle for all the kind of backward, forward, or radial blade. Okay. We are assuming that inlet velocity triangle. This is inlet velocity triangle. Now the change will be at the outlet velocity triangle. How will it look like for a backward curve vane? So for a backward curve vane, your phi is less than 90. Let me first make a triangle here. Let me use another color. Can I make like this? Okay, I'll make like this. Yeah, this will look fine. So we are saying that we have VF2 low velocity. This was your absolute velocity at 2. This was your wall component VW2. This complete is U2 at the second point, and because of the presence of relative motion, so it will be VR2. Okay. And what was the angle? This was your angle phi, which is less than 90 degrees. And this was your angle beta. This is your angle beta, main angle at outlet. Sorry, beta, alpha and beta were there. No? So alpha here is how much? 90 degrees at the inlet, and beta is some another value. So alpha was your nozzle angle at the inlet, and beta is the diffuser angle at the outlet. So our alpha will be 90 degrees at inlet. Okay, this is your phi less than 90 for the backward curve vane. For a forward curve vane, it will be forward blade. It will look like this. Let me make the velocity triangle here. Right triangle. Okay. This. Okay. So this is your absolute velocity V2. Okay. We have another point like this. So this is our angle phi, which is greater than 90 this time. Okay. The component of V2 is VF2, and this is VW2 from here till here. VW2, whereas your U will be this time from this to this. Okay. U2, and the relative of both of them will be VR2. These satisfy all the conditions which we have built in the previous tutorial. Okay, and this will be your angle beta. Okay, at the outlet. Whereas your radial blade, the third category, will have your phi is equal to 90 degree. Here phi was greater than 90. The radial blade will look something like this. Okay. So this is your absolute velocity V2. Your phi is exactly 90 degrees. Your beta is this one. The flow component VF2, and this is VW2, which is equal to generally VW2, which is equal to U2 itself. Okay, U2 itself. All right, let me just track this figure. So what was your Euler work expression? That was VW2 U2 minus VW1 U1. Euler work was, which we have derived in the previous tutorial, it is VW2 U2 minus VW1 U1, and we have said that the wall component at inlet is 0. It is nothing but equal to VW times U2. This is your work input, and power input will be mass flow rate into VW2, that is in watts. Okay. Any doubts still here to anyone? Now we will come to the situation of slip. What do we mean by a slip in the fluid? Just give me a minute, please. I'll do that. All right. If no doubts, we can proceed further to the topic of slip. Right here. So we have seen the velocity triangle. What do we mean by a slip? So what do we say that under an ideal condition, we assume that fluid particle exactly follow the blade profile. Okay, all of the fluid is following the blade profile. But in actual working condition, where you have number of blades, okay, they are finite in number attached to an impeller. Okay, so there is some air is also trapped between the blades. Okay, when the blades are moving. So air is trapped between the blade passage due to inertia, which creates a pressure difference across the blade. Okay. When the blades are moving, because of the inertia, the air is being trapped between the blades. The whole fluid is not able to follow the complete blade profile because of the pressure difference of the air and the fluid. Okay, pressure difference between the fluid particles, which are that basically deviates from the ideal path, and this deviation is known as slip. Let me write here under ideal condition. We assume that the fluid particles exactly follow the blade profile but in actual working condition, where number of blades are finite, some air is trapped between blade passage due to inertia effect, which creates pressure difference across the blade, and due to this pressure difference fluid are deviated from its idle path. This deviation is known as slip. Think of it like that. You are moving in a straight line with some another people. Okay. There was no change in the no disturbance in your inertia, but suppose some of the person or some wind blow at a very high speed. Okay, then you are getting dragged and you are not again in the straight line. You are not able to follow that straight line. Okay, so because of that pressure difference, uh, you are not able to follow the same path, idle path, and this you will slip from your idle condition. So the actual effect of the slip, it is decreased. That means that actual blade angle at the outlet, which ultimately reduces, and the wall component at the outlet. What do I mean by that? The actual effect of slip is, note, slip is decreases actual blade angle at outlet, which ultimately reduces wall component at outlet. Okay. So what slip is basically? Slip is nothing but equal to U2 minus VW2. So how was your velocity triangle at the outlet looking like? So this was your V2, then I had VF2, VW2. This complete was U2. Okay. This was your angle phi. This was VR2. So U2 minus VW2 is basically your slip. This is your slip. This region. Okay. U2 minus VW2. If it would have been a radial blade at outlet, then U2 would ideally be equal to VW2. But because of the slip, the U2 is a bit higher compared to VW2, and it leads to a increase in the decrease in the actual blade angle, okay, at the outlet. All right. And there is a term which is also called as slip factor. Slip factor. Slip factor. So your slip factor is nothing but ratio of the work done under the theoretical condition when number of blades are finite to the work done under the ideal condition. Define as ratio work done under theoretical condition, that is your ideal condition, the number of blades are finite. You cannot have infinite number of blades. Okay, when number of blades are finite to the work done under ideal condition. Okay, that, what do I mean by that? Slip factor sigma is nothing but equal to, sigma is equal to VW2 U2 was your work done under the ideal condition to that of, sorry, the theoretical condition to that of ideal condition VW2 U2, and here it will be equal to U2 square, because radially, if it would have been a radial blade, then U2 and VW2 would have been equal, but there was a deviation, that is why there was a difference in the velocities that lead to a slip. Okay, this is nothing but VW2 U2 by U2 square, and that is VW2 by U2. Okay, VW2 is a lower value and U2 is a higher value if you see from this diagram. U2 is a bigger value. Okay. So Euler work is nothing but, sorry, Euler work was nothing but VW2 U2, and this can be written in terms of VW2 can be written as sigma times U2 times U2. VW2 can be written as U2 times sigma. Okay, so it is sigma times slip factor times U2 square. Okay, that is your net work input in terms of slip factor. In terms of slip factor, there is one another term, that is power input factor. Power input is mass flow rate into work input. What will be a power input factor? Power input factor denoted by a symbol psi. It is defined as the ratio of actual work input to idle work input. And due to frictional losses, the actual work input is always greater than the idle. Generally, the values varies from 1.03 to 1.05. Due to frictional losses, the actual work input is greater than work idle. Okay. Generally, psi lies between 1.03 to 1.05. Okay. So psi is nothing but actual work input to that of idle work input. And what is actual work input? It is mass flow rate time VW2 U2. Okay. That is mass flow rate time slip factor times U2 square. Okay. So idle was when sigma is this is your idle work input. Sorry, let me again write this. I missed something. So actual is you want to get, you don't know what is actual work input. You know theoretical, you know the idle. So so your slip factor was theoretical to that of idle. Okay, and idle is mass flow rate times VW2 U2. Okay. So actual will come out to be psi times mass flow rate into V2 is nothing but sigma time U2 square. Sigma, if sigma is 1, if there is no information regarding sigma and psi, always take it as 1. Always take it as 1. From here you get the actual work input. Then there is also an isentropic efficiency of a compressor. Let me write a short term here. Isentropic efficiency of compressor. So if we see from the temperature entropy plot, which we have already discussed, for the compressor, if the compressor is isentropically compressing from stage 1 to 2 and then delivering, okay, using an polytropic law, and finally the suction process. So But in actual scenarios, there is a presence of friction. So the entropy is going to eventually increase, not from 1 to 2, but from 1 to 2 dash. Okay. So this will represent your temperature in terms of stagnation. I can say that T naught 2 dash, this is T naught 2, and this is T naught 1. So efficiency is always higher to lower. So isentropic efficiency of a compressor is nothing but higher value is T naught, sorry, lower to higher, sorry. Efficiency is lower to higher. So T naught 2 minus T naught 1 to that of T naught 2 dash minus T naught 1. There is also a scenario of a pre-wall in the combustion chamber. As I've said that there is a lot of high stress scenarios happening. So for the compressor which are running at a very high speed, there is a possibility of the shock waves at the inlet and at the inlet of the compressor. And if the value of the Mach number is greater than 1, then fluid is given a pre-rotation with respect to the fixed guide blade at the inlet of the compressor. And due to which there is a situation of the introduction of a whirl component at the inlet, then you cannot say that your VW1 will be 0. You will have a whirl component at the inlet with a decrease in pressure and increase in the construction cost, which eventually leads to the so, pre-wall in centrifugal compressor. Pre-wall in centrifugal. So far, we have not come to the axial flow. We are dealing with the centrifugal compressor. So rotary compressor have two, centrifugal and axial flow. Centrifugal compressor. So for the compressors which are running at very high speed, there is a possibility of shock waves at inlet, and if value of the Mach number is greater than 1, then fluid is given a pre-rotation with respect to fixed guide blade at inlet of compressor, due to which there is a introduction of wall component at inlet with a decrease in pressure and increase in construction cost. Okay. Then what will be your work input in that scenario? Let us say our first note will be the work input will now become VW2 U2 minus VW1 U1. Now VW1 won't be 0. And the pre-wall angle are mentioned with respect to the axial direction, and they vary from a 20 to 25 degrees. For a general note point, pre-wall angle, I'll tell you what is pre-wall angle, are mentioned with respect to axial direction. and generally varies 20 to 25 degrees. So let me make the diagram at the inlet. So this is your velocity component, the V1 absolute. This is VF1. This is VW1. This was relative. And this whole is your velocity U. This was your angle alpha. Okay. The pre-wall angle is nothing but this angle. Okay. Pre-wall angle. Okay. Pre-wall angle. All right. I think this is clear. This is angle theta. That's very good. Okay. Now we are finished with the centrifugal compressor. Any doubts still here? So that we can start the axial flow compressor. Okay, no doubts. Axial. Axial flow. So here basically your inlet velocity and outlet velocities are going to be same. That is U1 and U2 I'm talking about. Okay. Let me draw a diagram first so that you all can visualize. So here your rotor looks like this. I'm showing you the front view. Okay. Not the front side view. So this is an axis of your rotor. This complete is your rotor or impeller. What do you want to say? There is a casing. This is your casing or stator. And there are blades over this rotor. So blades are like this because rotor is moving at some velocity omega. So this is a moving blade MB. Okay, and there is a fixed plate here, fixed blade over the casing to be act as a diffuser. And this combination of moving blade and a fixed blade is called as a stage. One stage. Fluid is entering from here. Fluid entry. Okay, fluid is entering from here. So fixed blade, moving blade is one stage. Another fixed blade, moving blade. So there are multiple number of stages. Okay. Then again a fixed blade, then again a moving blade, then again a fixed blade, and so on. This all goes on. Okay. And from here the fluid leaves. Finally. Okay. Fluid enters and fluid leaves. So it entered axially. So this is your axis. That is why I'm saying axially it entered, axis of the rotor or impeller. It entered axially and exited axially as well. Okay. So impeller is a region of the moving blade and casing is a basically a having fixed blade is a diffuser. So what happens in axial flow compressors? It consists of row of moving blades mounted on the circumference of the rotor and row of fixed blades mounted over the casing. In axial flow compressor, fluid enters along the axial direction of the machine and it consists of number of stages. Each stage consists a set of fixed and moving blade, and cross section between the blade is of a diverging type. Okay, cross section between blades is of a diverging type. There is a rise in the static pressure. So let me first write these points. It consists of row of moving blade can be mounted on circumference of rotor and row of fixed blades that is FB mounted on casing. Okay. In AFC, axial flow compressor, I'm writing the short form. In AFC, fluid flows along axial direction. Okay. And consist of axial direction of the machine, and it consists of n number of stages. Each stage consists of a set of set of fixed blade and moving blade, and cross section between blade is diverging type. So this is all about the design of a axial flow compressor. Okay. Now how the work, that is a Euler work VW2 U2 minus VW1 U1 is derived, as we have derived in our centrifugal compressor also, that expression for a not in centrifugal, during the principal explanation of the principle of rotary compressor in the previous tutorial. So there is a rise in the static pressure due to the diffuser effect in the moving blades, and also there is an increase in the kinetic energy, which is further connected to the pressure rise in the fixed blade, that is your diffuser effect. Okay. But here the velocity u1 and u2 are equal in axial flow compressors. Okay, your velocity u1 and u2 are equal, so there won't be centrifugal effect. That was u2 square minus u1 square. We had impeller effect, we had diffuser effect, as well as a centrifugal effect. But the centrifugal effect will be zero because velocity at inlet and outlet is equal. Okay. So the pressure rise is having a lower value for axial flow compressor compared to the centrifugal compressors. Okay. Let me say, write the Euler work was nothing but VW2 U2, VW1 U1, nothing but V2 square minus V1 square by 2. That is your impeller effect, plus U2 square minus U1 square by 2. This term is 0. U1 is equal to U2 plus VR1 square minus VR2 square. That is your diffuser effect. Okay. So it is only sum of impeller plus diffuser effect. So there is a, let me write the point. There is rise in static pressure due to diffuser effect in moving blades, and it also increases the kinetic energy, which is further converted into pressure rise in fixed blade, the pressure rise is having a lower value. Is having lower value for axial flow compressor. Lower value axial flow compressor. Okay. So in each stage, the pressure rise will be less than 2.3 bar, let us say. That is why we required a multi-staging to happen. That is why number of stages are there. So first stage, second stage, third stage, and they are diverging in section as well. Okay. So that is why to achieve a higher pressure at the outlet, we need to have a multi-staging to happen. Okay. So how the velocity pressure diagram will look like here. Let me make that again. One. Let me draw it directly itself. 2, 3, 4, 5, 6. Okay. So velocity above, okay, and pressure below. Okay. The first stage is the fixed blade, then moving blade, one stage, then another stage, fixed blade and moving blade, then another stage, fixed blade, moving blade. Okay. So in the fixed stage, the velocity decreases first. Then in moving stage, the velocity increases. This is your first stage happened, and pressure increased in both of the scenarios. Okay. So pressure increased in the fixed stage as well as the moving stage. Again, fixed stage, velocity decreased, moving stage, velocity increased, decreased, increased. But the pressure is continuously rising in all the stages. Let me draw the pressure line once again. The pressure is continuously increasing. Let me write the note point. First note says the pressure rise for per stage for axial flow compressor is having a lower value and generally varies from 1.2 to 1.4, whereas for a centrifugal compressor it is 4 to 6 bars. Okay. The pressure rise per stage for axial flow compressor is having lower value and generally one point two to 1.4 bar, whereas for centrifugal compressor varies from 4 to 6 bar. Okay. In case of the compressor, the axial flow compressor, the blade height decreases. Sorry, in case of the compressor itself, not only the centrifugal, the blade height decreases from inlet to outlet, and as the pressure increases, the density increases. And in order to maintain the constant axial flow, so for axial flow compressors, the blade height is decreasing, not for the centrifugal I'm talking about. For the axial flow compressor, the blade height continuously decreases. And as the pressure is increasing in every stage, if you see the blue line, the density is also increasing. P is equal to rho RT. Okay. And in order to maintain the constant axial flow velocity, of the blade needs to be decreased, because flow is nothing but flow rate is rho into area into velocity. If area of the blades are same and if density increasing, the velocity has to decrease to maintain a constant flow rate. Okay. So let me write in case of, not in case of, the height of blade, because in centrifugal compressor your diagram was like the pressure was increasing. If I show you the centrifugal diagram, pressure diagram, pressure was first decreasing, increasing, and then increasing further. But here from the start itself, it is continuously increasing. The height of blade decreases from inlet to outlet as pressure increases, density increases, and in order to maintain constant axial flow, velocity of blade decreases. Since mass flow rate is nothing but rho into area into flow velocity, if rho is increasing, the velocity of the flow has to decrease. Okay. Oh, sorry. If you want to maintain axial constant velocity, sorry, my bad. I mistyped here. Constant axial flow velocity. Constant flow axial velocity. If you want to maintain the constant velocity in the hole, then your area needs to be decreased. Area of blade needs to be decreased. How? Mass flow rate is rho into area into V flow. If you want to maintain it constant, the density is already increasing. Your area should decrease. Okay, to maintain the constant flow velocity. Okay. So how will your blade height will look like? How will your blade look like? So blade height will continuously decrease. Okay. So this was the inlet. Now you understand why do we make the diagram of compressor like this, whereas in turbine the diagram was like this, the schematic diagram. There the blade height is increasing. This is your outline. Okay, and these are your heights. What will be the cross section area at any point of the blade? Okay, how we will get to know, because your area is continuously decreasing. Basically, your height of the blades is decreasing. So how will you get the cross section area at any point? Let me write cross section area at any point. So let me tell some terminologies. Let us assume your RT is your tip radius, your RH is your hub radius, H is the height of blade, and dm is your mean diameter. Okay, mean diameter. So let me tell you in the diagram, use some another color. So this is your RH, and this is your, suppose this hole is going from like this. So this is your RH. Okay, hub diameter. Okay. And RT is your tip radius. Hub radius and tip radius, RT and RH. So the RT, Y and tip radius and up radius. So what will be your height? It will be the difference of two. That is your height of the blade. This is your H. Therefore, height will be RT minus RH. And in terms of area, it will be pi by 4 dt square minus dh square. Okay. So let us write by bifurcating it in terms of A plus B formula. Dt plus dh by 2 into dt minus dh by 2. Okay. 2 and 2 is 4 and A plus B into A minus B. So this is nothing but your Tm, and this is nothing but your height because it's in terms of diameters, not radiuses. Area is nothing but pi dm times height, pi dm h. This is your final expression of the cross section area at any point. So you need to have a mean diameter and the height of the blade. So let us write few note points here. The first note says, in axial flow compressor, the fluid enters and leaves in same direction. So that means your u1 and u2 velocity will be same, and it will be equal to pi into mean diameter into rpm by 60. In AFC, as fluid enters and leaves in same direction, u1 is equal to u2 and it is equal to pi d mean into n by 60. For design consideration, we say that our we have zero axial thrust on the bearings. So that means the velocity of flow at the inlet is equal to outlet. Okay. Again, radial blade scenario I'm talking about. There is no ball component. If I say, then there will be no thrust. So for design consideration, for less stresses, for design consideration, or zero axial thrust on the bearing, assume Vf1 is equal to Vf2. Next point, all the angles, that is your alpha, beta, theta, and phi. Here we will deal in terms of alpha 1, alpha 2, beta 1, beta 2. All the angles alpha 1, alpha 2, beta 1, beta 2 are measured with respect to axial direction. Okay. So alpha 1, alpha 2 are the absolute velocity angle at inlet or outlet. Alpha 1, alpha 2, absolute velocity angles at inlet and outlet, and beta 1, beta 2 are moving blade angles at inlet and outlets. Okay, moving blade. Okay, so how alpha 1 and beta 1 will look like if I want to show you. So suppose you have a velocity triangle like this. So this is your alpha 1 and this is your beta 1. Okay, absolute velocity and moving blade angle at inlet. Similarly, it will for the outlet. Based on these three conditions, we can make our inlet and outlet velocity triangles. Okay, next point, inlet velocity and outlet velocity triangles are same by above three condition. Above three conditions. So let me say again, let me make the triangle. Yeah. Okay. So this is your absolute velocity V1. This is VW1. This is VF1. This is VR1. This whole is U1. This is alpha1. This is beta1. Okay, alpha1, beta1. Let me name the triangle as A, D, C, and D. I'm talking about the triangle in triangle ADC. ADC, this triangle. Okay. From Pythagoras theorem, I can write AD square is AC square plus CD square. What is AD? AD is your VR1. AC is VF1 and CD is this much, that is U1 minus VW1 plus U1 minus VW1 whole square. Expand it, you will get VF1 square plus U1 square plus VW1 square minus 2 U1 VW1. Okay, this is VR1 square. Okay. Then let us rewrite together. Your VR1 square will be U1 square minus 2U1 VW1, and taking this and this together, VF and VW is nothing but V, total absolute velocity. Okay, plus V1 square. Okay, then we can transpose it and write U1 square plus V1 square minus VR1 square is equal to 2U1 V1 2U1 VW1. So from here, your VW1 U1 will come out to be V1 square by 2 plus U1 square by 2 minus VR1 square by 2. I'm again deriving the same scenario which we have derived in the principle of the rotary compressor working in the previous tutorial. Similarly, you can get VW2 U2 will be V2 square by 2 plus U2 square by 2 minus VR2 square by 2. Now you will write your Euler work, that is, therefore in AFC, that is your axial flow compressor, VW2 minus VW1, because U1 and U2 are same, so I can write it as U. It will be V2 square minus V1 square by 2 plus U2 square minus U1 square by 2, that get cancel out because U1 and U2 are same, and VR1 square minus VR2 square by 2. Okay, this is because of the presence of the fixed blade, and this is because of the moving blade. Okay, diffuser effect. And okay, now let us define one terminology that is called as degree of reaction. Degree of reaction is nothing but ratio of enthalpy rise across the moving blade to that of enthalpy rise across one stage, complete stage. Okay. It is defined as the ratio of enthalpy rise across moving blade to that of enthalpy rise across stage. Okay. So the symbol for it is RD, R subscript D. So RD is nothing but change in enthalpy across moving blade to that of change in enthalpy across the stage. Okay. Moving blade enthalpy change can be written in term of velocity is nothing but your this term, and whole of your enthalpy rise across each stage is the complete this VW2U minus VW1 times U into 2, okay, for each stage. So that is VR1 square, VR2 square by 2. This is your moving blade, and whole is VW2 U2 minus VW1 U1. So this can be written as VR1 square minus VR2 square by 2 times VW2 minus VW1 into U, because U1 and U2 are same. This is your degree of reaction flow, axial flow compressor. Okay. Now let us see again the above same diagram. Let me copy this again once again. Copy. Let me paste it here for a velocity triangle. Okay. Okay. Let me write the velocity triangle once again. This is, I guess this is wrong. I'll again make it. This is right. Perfect. What happened? Why the color changed? All right. A, B, C, D. Okay. So if you see the what was your work? Work is nothing but VW2 minus VW1 times velocity U. Velocity U. If you see from the figure, tan beta, tan beta 1 is nothing but CD by AC. CD by AC. And CD is nothing but your U1 minus VW1. And AC is your VF1. So U1 and U2 are same, U minus VW1 by VF1. Okay. And flow velocity we have also assumed to be equal. Okay. For no thrust across the axial direction. So this is your tan beta 1. So from here, your VW1 can come out to be U minus VF tan beta 1. Similarly, if you see the other triangle at the outlet, similarly, your VW2 will be U minus VF tan beta 2. Okay, put this, let us say this equation was 1, this equation is 2, this equation is 3. Put 2 and 3 in 1. You will get your work as U minus VF tan beta 2 minus U minus VF tan beta 1. Okay, so it will be u times Vf and beta 1 minus beta 2 per stage. And this is for each stage. For n number of stage, it will be n times UVF and beta 1 minus tan beta 2. Okay, that will be your total work. This n is your number of stages. Okay, number of stages. So again, you can put this expression in degree of reaction RD. That was nothing but VR1 square minus VR2 square, so that of 2 times U VW2 minus VW1. So it will be VR1 square minus VR2 square, but times 2 U, and VW2 minus VW1 can be written as 2 UVF tan beta 1 minus and beta 2. Okay, all right. Let us get VR1 and VR2 also. So if you see from the diagram, if I want to calculate cos, so cos is nothing but Vf by Vr1. Okay, Vf by Vr, cos beta. Since cos beta 1 is Vf by Vr1, this implies your Vr1 will be Vf times secant beta. And similarly, Vr2 will be Vf time secant beta 1 secant beta 2. Put these values above. So your degree of reaction will be Vf square secant beta 1 square minus secant square beta 2. So that of 2 UVF times tan beta 1 minus and beta 2. Vf cancel out. So we are left with, and secant can be written as 1 plus tan beta square, tan square beta. Okay, since 1 plus tan square beta from trigonometry can be written as secant square beta. After putting all these values, you will get your final degree of reaction will be tan beta 1 plus tan beta 2. This is your final expression in terms of the angles. Okay, if I want to calculate what will be the condition for 50% degree of reaction. Okay, what do I mean by that? Is basically how much the enthalpy rise has changed across the moving blade is half to that of the enthalpy rise of complete stage. Okay, it means that. So condition for 50% degree of reaction, 50% RD. Okay, that is your RD is 1 by 2. I mean by this. Okay, so let us get the conditions as well. So your RD is Vf from above in the red box times 2u tan beta 1 plus tan beta 2. I'm just adding and subtracting tan alpha 1 from both of them. Tan alpha 1 minus tan alpha 1. So the expression remains the same itself. Okay. So let us get tan beta. So again, let me draw that figure, paste that figure here, or let me draw one more figure separately. This is your triangle A, B, D, this was your C. Okay. So let us say this much is X, your BC is X, and let us say your CD is Y. Let us say like this. Okay. All right. This was your alpha 1. This was your beta 1. Okay. Alpha 1 and beta 1. Okay. So what will be, let us say, this is VF. Chandana, any doubts? You have unmuted yours. Okay. This was your VF. All right. This was your V1. So let us say what is tan beta 1? Tan beta will be CD by AC, that is Y by VF. So VF by 2U, tan beta 1 is Y by VF, plus let us keep tan beta 2 as it is. What will be tan alpha 1? It will be X by VF. Okay. Plus X by VF, and let us keep tan alpha 1 as it is. And alpha 2, not alpha 1. Okay. Oh, sorry, tan alpha 1 only. I subtracted and added the same term. My bad. Tan alpha 1. One time tan alpha 1 I have written like this, X by VF, and another time tan alpha 1 I am keeping like this only. So it will be VF by 2U. It will be X plus Y by VF plus tan beta 2 minus tan alpha 1. You will understand why I'm doing like this. Okay. X plus Y is nothing but your complete U. Okay. So X plus Y is U. So it is VF by 2U times U by VF plus tan beta 2 minus tan alpha 1. Okay. For 50% reaction, you need to keep RD equal to half. Okay. So it will be what? 1 is equal to, so this and this term cancel out. So it will be 1 is equal to VF by U times U by VF plus tan beta 2 minus tan alpha 1. Okay. Take this on the right left hand side. U by VF is equal to U by VF plus tan beta 2 minus tan alpha 1. So this and this term cancel out. That means your tan beta 2 is equal to tan alpha 1. This implies your alpha 1 is equal to beta 2. This is your first condition. Similarly, you can get the another condition from the outlet triangle. Your alpha 2 will be equal to beta 1. This is your another condition. Okay. So first absolute is equal to others relative. Again, if you see, if alpha 1 and beta 2 are equal from here, then what you can write? Cos of alpha 1, because these are very low values, so cos of alpha is equal to alpha. So cos of alpha 1 is equal to cos of beta 2. And what is cos of alpha 1? If you see from the diagram, it is Vf by V1. Vf by V1. And cos of beta 2 is Vf2 by Vr2. So this is Vf by Vr2. Okay. I can write it as Vf by V1 is equal to Vf2 by Vr2. So this and this cancels. So therefore, your condition is V1 is equal to Vr2 And from here, your condition will come out to be V2 is equal to VR1. So these are the other two conditions also. So there are four conditions for 50% degree of reaction. 50% degree of reaction in axial flow compressor. Axial flow compressor. All right. We can also derive the degree of reaction for centrifugal compressors also. We have not derived earlier. So let me derive. It will take a minute. RD for centrifugal compressor. Let me write. So what was the expression of RD? It was U2 minus. So here one another term will also be there, that is U2 minus U1. Okay, this time it is not only VR1 because U1 and U2 are different in centrifugal compression. So it will be U2 minus U1 square by 2 plus enthalpy change in the moving blade plus VR1 square minus VR2 square by 2 to that of complete stage, that is VW2 U2 minus VW1 U1. Okay. So I can write this expression as VW2, this above numerator can be written as VW2 U2 from the Euler work minus VW1 U1 minus V2 square minus V1 square. We have derived the Euler work already by 2 to that of VW2 U2 minus VW1 U1. Separate both the numerator terms. So it will be 1 minus V2 square minus V1 square by 2 times VW2 U2 minus VW1 U1. Okay. If I'm saying my wall component is 0 in centrifugal compressor, where I have taught, since, not since, let us say if my wall component VW1 is 0 at inlet, so RD will be 1 minus V2 square minus V1 square by 2 times VW2 U2. And V2 can also be written as VW2 plus VF2. Okay, absolute velocity is wall plus flow. So that is 1 minus VW2 square, VW2 square plus VF2 square minus V1 square by 2 VW2 U2. If I assume that my flow velocities are same, if VF1 is equal to VF2, then my reaction degree of reaction will be 1 minus VW2 square. Have I written something? Huh. Okay. Yes. And if it is a radial velocity, so VF1 and VF2 both will be equal. So this is VF2 square and VF. What do I mean here is that at inlet and outlet, my VF1 and VF2 are equal, and wall component is 0 at the inlet. So VF1 and VF2, that is V1 and VF2 will be equal, and we are left with VW2 square by 2 VW2 U2. So 1 and 1 cancel out. So we are left with 1 minus VW2 by 2 times U2. If I want to say for radial blades at our outlet, the degree of reaction will be for radial blades at outlet, my VW2 will be equal to U2. So if you put in this above, it will be 1 minus 1 by 2, that is half, that is equal to 50% degree of reaction. This will be the condition. Let me show what I am trying to say. Some students might get confused. This was your blade. Okay. This was your V1, which was equal to VF1. Okay, because while component is 0, this is velocity u1 and this was vr1. Okay, then at outlet I'm assuming that it is a radial again. So this was v2 is equal to vf2. Okay, this was vw2 which was equal to u2, and this was relative velocity at 2. That's why I'm able to say this. Okay, all right. So I have completed the complete course, IC engines and gas turbine, in very detail, all the topics. Okay, you can go through the assignment, the last assignment for this. You will have the questions. This was the last tutorial for this course. Okay, my if you have registered for the course, you can see the links for all the videos of these recordings, the YouTube links, as well as the Google Drive link for the PDF of the notes by the NPTEL team, shared by NPTEL team in form of a Google Sheet. If you are new, you can directly check through my YouTube channel. That is, the name of the YouTube channel is NPTEL with Varnit. YouTube, right? The name is NPTEL with Varnit. My name is Varnit Kapoor, and I'm doing my PhD from IIT Delhi currently. And in each video for the corresponding playlist of the course, you can see the video description. You can see in each video description there is a link of the Google Drive where you can see the notes of the PDF. So this is
Is it is it over, sir? Hello, hello, sir.